Yes, good evening everyone. So, welcome to this discussion class Week-8 for the course of Design of Photovoltaic Systems. This course is being taken by Professor L. Umanan from Department of Electronic System Engineering, IISc Bangalore. And I am Ravi Kumar, a PMRF Research Scholar at IIT Bombay. So, before moving to the class, first let's recap what we have understood till now. So, we have seen what is solar photovoltaic is. Cell is, then we have also understood what is solar PV module. Then we have seen the IV characteristics. Which like this. So on this IV characteristics, we know this is our ISC, this is our VOC, and here power is 0, power here is also 0. So in between there is a point like here at which power is maximum, and this is known as maximum power point. So to find this particular point, we have seen that we have different DC to DC MPPT tracker, and we have understood how they works, and we have seen how can we control these MPPT trackers to work only in this region. Particularly we have seen buck, boost, and a combination of buck boost converter. So this is all about our recap. So here what we are seeing that from the PV side, like PV module, we know how to work or how to get the maximum power. But like other than this PV, we have battery connected to these PV modules. So these are batteries. So particularly in this week, we are going to study how PV module are integrated with these batteries. So in this particular week, we are seeing PV battery interfaces. So there are two scenarios, like one is, can we connect a battery to the PV module directly. Second, if not, then how do we connect a battery to the PV module? So first of all, we will see, can we connect a battery directly to a PV module, and then we will see, if not, then how can we connect a battery. So this is the agenda for today's class. So first of all, let's understand the battery characteristics, because we already know IV, that is the PV characteristics, and we also need battery characteristics to connect them. Connect, or we can say interface. So let's see what are the battery characteristics are. So first of all, we will see direct PV battery connection. It means directly we are connecting a battery to a PV system. So let us consider this is a battery. Why this is a battery? Because battery is a constant voltage source. So here it is voltage VB, and there are some internal resistances inside a battery. That's why we have this RB, that is the resistance of the battery, and it is connected in series. So this particular combination is a battery. So with a voltage source we have some resistance, and this VT is the terminal voltage of the battery, and IB is the current which flows inside a battery. So in charging we need to put current to the battery. While discharging we will get the current out of the battery. So these are the two things. If we are like giving some current IB to this battery, so the minimum potential, or we can say the VT, minimum potential which is required to charge the battery will be VT equals to VB plus IB RB. So this is the potential which we require while charging. Now let's see how, like, what is the characteristics of a battery is. So while charging we have this VT equals to VB plus IB. This is our voltage axis, this is our current axis, voltage axis, and this VT is the out terminal voltage of the battery. So this VT is greater than VB because we have VB plus IB into RB equals to VT. So in this case our characteristics will look like this. This is the characteristics, because at current 0, when IB equals to 0, so the terminal will voltage of this battery will be equals to VB, and when I will increase, VT will become equals to VB plus IB RB. That's why this is the characteristics on a slope, and this slope is directly proportional to this internal resistance, and this distance which is like increasing with current, it is the IB into RB voltage. So at any point we can calculate this IB into RB by measuring this distance. So this is all about the charging. Now let us see what happens when we discharge a battery. So in this case this is the battery. Now we are discharging, means we are taking current out of the battery. So this direction of this IB will be reversed this time, and we have VT is the terminal voltage. So this terminal voltage will be equals to the actual VB minus IB into RB, voltage across this resistance, and this will be the VT with relation with VB and IB into RB while discharging, means we are using the battery at this condition. And how it IB characteristic will look like. So while discharging, the same thing, at IB 0, VT equals to VB, this is the point which is equals to VT, and when it is discharging, so this, in this case it is negative, so our line at angle will be this side because it is less than this VT. So this is the case while it is discharging. Now we already know that IB characteristics is like this. So now we will try to fit this particular IV characteristics with battery characteristics like this. So this is a characteristics of solar PV plus battery. Here you just understand one thing. So this is the IV characteristics, and in case of charging, this is the characteristics of battery, and this is a particular point VB. So when this battery is being charged, so this VB will increase. VB is the voltage of battery, it will increase. So because this VB will increase, so this point will shift this side, and while this point will shift this side, this entire characteristics will be here only, and now current will reduce. So it is automatically controlling the charging of the battery. Whenever their battery is being charged, so this IV characteristics is adjusting the currents. In that situation, the current which is flowing inside a battery will be less. So like we are here to see, this particular combination is the best for the battery, because while charging it is automatically controlling the current which is going inside a battery. But see, what are the constant here? We will see in the next slide what are the constant here. So let us understand one example, which is an example of direct PV battery connection. So we are considering lead acid battery with 12 volt nominal, 20 ampere hour is the capacity, and C10 is the charging rate or discharging rate. VB is the 10.8 volt. VB is while discharging, means it is the minimum voltage of the battery, and while charged this is the maximum voltage of the battery, and maximum charging current can be 2 ampere. So let us see how this battery can be connected with the solar PV system. So this is the combination of this IV characteristics of the battery and the PV system. So this is the current which a battery can take maximum. So it is the point when battery is completely discharged, and when it will charge, this will move this side, and this is the condition when it is fully charged. But here one constraint is that the IMPP or maximum power current of solar PV should equals to 2 ampere. That is the capacity of our battery. And also this VOC, I am writing here only, this VOC should be greater than or equals to VB maximum. So if like the characteristics of the battery, the IMPP and this VOC condition of the battery is matched with the PV module, then only we can directly connect this PV battery connection. But if it is not like having the same condition, or we can say the battery maximum charge and this VB, or we can say the VOC is different, then we need some charge controller between this PV panel. So this will be the scenario now. This is our battery. This is our PV module, and this is our charge controller. So in this condition, this configuration will be followed. In this particular configuration, we have 3 different components. So let us understand this thing as well. So indirect connection of the PV battery connections. What we have a PV module connected with a battery and then connected with a load, and here we have switches. So this is the configuration, and in this configuration we have this Vmax of the battery, Vmax, Vb at any point of time. The Vb is the voltage across the battery, and V minimum is the particular point. So we have three different voltages of this battery. Vb, that is the voltage of battery at any point of time. Vmax, that is the maximum while it charged. V minimum is the minimum when it is completely discharged. So when it is completely discharged, then it should be disconnected from this load and it should be connected with this PV module. It is very simple. While our battery is fully discharged, it should not connect it to the load, it should be connected to the charger only. Second condition, when it is maximum charge. So in this particular situation, our battery is fully charged. So now our battery should not be connected to this charger, it should be connected to the load only. This is the second condition. But when this Vb is between this V minimum and V maximum, it means our battery is neither fully charged, neither fully discharged. Then it should be connected with the both, this charger as well as the load. So here charger is our solar PV system. So these are the conditions which I just told you. So charge controller just control these three conditions. First condition is that voltage of the battery is greater than the Vmax. So it will disconnect the battery from the array. It means our battery is already fully charged. Second situation says the Vb of battery is less than the V minimum. It means our battery is fully discharged. So it will be disconnected from the load. And third condition says this is in between. It is neither fully charged nor fully discharged. So it means it will be connected to the both array as well as the load. And this should control that our V minimum should be this side of this point and V max should be this one. So this is the particular thing which a charge controller controls as well. And even we can have a DC-DC converter which makes this solar circuit to work between these 2 points only. And these 2 points are the V minimum and the V maximum. So in graphical way, I can show here. So this is the condition when Vb is more than the V max. It means our battery is fully charged. So it is disconnected from this solar PV system and it is connected to the load. So this current, this is the direction of the current which is flowing. Second condition, when this Vb is less than the minimum, it means it is fully discharged. So it is disconnected from here and it is connected here. So in this condition, battery is being charged. Then we have third condition, when this is in between, it is neither fully charged nor fully discharged. So in this particular condition, this solar PV array is also connected. This load is also connected to the battery. So these are the functional logic which a charge controller uses. Okay, so this is all about in this week. So now we will solve few questions. So first question says, identify the below characteristics, and these are the options. This particular characteristics is showing what? Okay, Rasmi said C, that is battery charging. Yes, absolutely. Because we have Vt equals to Vb plus Ib Rb. It is positive sign, so it will go particularly this direction. So it is battery charging. In case of discharging, it will be like this. I am plotting here only. So it will be the discharging one. So here it is charging, and here it will be discharging. Yes, C is the correct answer here. Now let's move to the next question. It says, what is the terminal voltage of the battery when discharging? And these are the options. Okay, I'm getting the answer. Rashmi, Ramya, Vikas all are saying C. It is discharging, so it is a negative sign here. So yes, here this is for charging and it is for discharge. So correct answer is C. Now let's move to the next question. This is the very simple question. It says a battery with a 12 volt nominal voltage is connected directly to a PV module. Directly connected. The terminal voltage measured at the PV terminal is 11 volt at SOC 20% and 13.5 volt at SOC. It means charge or discharge state 100%. The IV characteristic of a PV module is shown below. It is asking what is the resistance value is measured from the PV terminals at the operating point C on its IV characteristics. Consider the curve between the operating points between A and B is approximately to a straight line. The current relation is given here and these are the options. Try to solve it and let me know the answer. The question is that at point C, what is RT, terminal resistance of this PV system? I'm giving you a hint. RT will be equals to 1 by slope. Here, green line slope. The slope of this green line will be equals to RT, 1 by slope. And how can you calculate the slope of this line? The straight line, the slope calculation of the straight line. Simple slope is calculated like this. Slope equals to our x is v. So in terms of x, if I write y2 minus y1 divided by x2 minus x1. So this is the formula for slope. What is y2? So let us consider one point here. This is what we are taking to this 2 and we are taking this point as 1. So what is y2? IC. What is the value of IC? See, we already given a relation. IC will be equals to 0.4 times IA plus IB. So can you get IC from here? Yes, 9.2. So 9.2, y1 is 0. What about x2? X2 is our VC minus 0. So our slope is coming 9.2 divided by VC. Now we need to VB. Why you are saying VB? We are at point C. We are looking, yes, VC. Okay, that's right. So now we need to get this VC. How can we get this VC? See, here clearly given, consider the curve between the operating points A, B is approximately to a straight line. So if I say this is a straight line like this here to here, so can you get the entire slope from here to here? What is the slope of AB line? I am writing here slope AB. What is the slope of AB? What is the slope of AB? Same thing, y2 minus y1. .64. No. So here we will be using the same formula, y2 minus y1 divided by x2 minus x1. So y2 minus y1, let us consider like 2 this point, in this case 1 this point. So we will have IA minus IB divided by VA minus VB, that is equals to 18 minus 5 divided by, what are the things at x? 11 minus 13.5. Five 5.2. That is even negative. So it is minus 5.2. Okay. Now what is the slope of AC? Slope of AC. Slope of AC. Same thing. IA minus IC, VA minus VC equals to what is the value of IA? 80 minus what is the value of IC? It's 9.2. What is the value of VA? It's 11 minus VC. Okay, right. Now let me know one thing. If this is the straight line from A to B, then slope of AB will be equals to slope of AC. Yes or no? These both slope will be equals. And if slopes are equal, then it will be equals to minus 5.2. And if it is 5.2, can you calculate VC from here? VC from here? What is the value of VC that is coming? No, not 9.31. It's so simple. Where is my calculator? Okay, I got your point. What you are not considering, you are not considering the negative sign. Consider the negative sign, you will get the right answer. Three is the like VC or the answer? I'm not getting this. Solve this for VC. What is the value of VC is coming? Because you are like taking the difference like yes, now you are right. It is 12.69 volt. Okay. Now come to this point. This RT will be the inverse of slope, and inverse of slope will be VC divided by 9.2. Put the value of VC. 12.69 divided by 9.2 will equals to how much? 1.38 ohm, and that is equals to 1.4. Then answer will be B. B is the correct answer here. Sorry. So we have correct answer as B. So we have calculated the resistance at the RT condition. Okay. Let's move to the next question, which says, in the last question, a boost converter is used as an interface, like here, it is shown here, between the PV module and the battery for fast charging by adopting a maximum power point tracking algorithm. If the operating point A, this one, it is the MPPT point, then at what duty value is the boost converter operated for the given values of the parameter and variables shown in the figure? It is just asking if it is the MPPT tracker working at a point A, then what should be the duty ratio value D. You need to calculate the D. These are the options. D in percentage term. It is just asking if this is the condition, the MPPT tracker is working here, then what should be the condition of D. So simple. See, here some current will be there, I, and here some current will be there, I. We take IB because it is the battery current, and it is the current which is from this PV module, and this PV module is at MPPT. So what is the current at MPPT? So we have I at MPPT PV module, PV side. Then we have V MPPT PV side. How much it is? It is clearly visible from this graph only, from the IV characteristics only. The voltage at A and current at A, yes, because it is 18 ampere and 11 volt. So we know this, that power will be same before the boost converter and after the boost converter. So power towards PV side will be equals to power towards battery side. What is the power towards PV side? What is the formula for power? Simplest formula for power. If we have current, we have voltage, then what is the power? Yes, 1.98 is the right answer. So here it is 18 into 11. Power towards battery. See, this is the particular thing towards the battery. So can you get the power? Power across the resistance, then power across the battery. Already I am saying IB is the current which is flowing through the battery. We have internal resistance of the battery. We have a VB, that is the battery voltage. See, we already know VT equals to I square B. So I into V plus VB, because it is charging. This we already know. In case of power, it will be power towards this battery side will be equals to I square B RB plus VB into IB. So I'm just putting this thing here. I square B RB plus VB IB. What is the value of VB given here? What is the value of VB? VB is 13.5. How? VB no, not from this circuit. I am asking this with the boost converter. Yes, 11. So it is like this. 1, what did you say? 9, 8 equals to I square B. What is the RB? 0.2 plus 11 IB. So we have I square B 0.2 plus 11 IB minus 198 equals to 0. Which kind of equation is this? This is a quadratic equation. Solve this equation and get the value of IB. Do you know how to solve this quadratic equation? We have minus B plus minus root B square minus 4 AC divided by 2A. These are the solution of X. This is the general formula. So A is this is A, this is B, and this is C. Put the value of A, B, C and find IB. Okay, I am just putting you at least solve them. B is how much? 11. So minus 11 plus minus I am taking because there will be two roots. There will be two solutions from this equation. One will be with plus, one will be with minus. Then root 11 square minus 4 0.1 into minus 198 because C is minus, divided by 2 into 0.1. What I am getting? Just solve this. 11 square minus 4 into 0.1 into 198, then add it because it negative will be positive. Take the under root, minus 11 divided by 0.2. One solution will be negative, one solution will be positive. Negative is not a feasible solution, so positive one will be there, a feasible solution. So feasible solution will be with this plus sign. Let me solve if you are not doing so. Not solving, you guys. Okay, 11 square, then plus 4 into 0.1 into 198. I am getting this 200.2 under root 200.2 14. Then I will just take the positive sign, means I will negative 11 divided by 0.2. I got my answer. It is 15.74. 15.74. So I'm getting IB as 15.74 amps. Now understand one thing. We have got this IB. We know this I. For the boost converter, what is the relation between this current, IB and I? Place 0.1 by 0.3. Yes. Is it 0.2? Where did I make mistake? It is 0.2. Yes. A is 0.2. Yes. Yes, Mama, you are right. So now what is the solution then? Eleven square plus 4 into 0.2 into 279.4 under root 279.4 minus 11 divided by 0.4. Okay, so I'm getting this 14.2 9. Are you guys getting the same or not? Okay, whatever it is, like if it is 0.2, 0.1, you can change this. So from here we have calculated this IB. We already know this I, and for the boost converter we have a relation this. This is IB, this is our I. So if I use this relation, I will get 14.29 equals to 18 1 minus D, and here you can get the D. What D you are getting? Point 0.21. Yes, then it is actually I calculated with the 0.1 only, so it is 21.5, around this 21. Yes, so it will be 21 percentage. And if we take this 0.2 as 0.1, I calculated using this 0.1 only, so you will get around 12. Yes, so like first of all you need to calculate this current at the both side, then from this relation you can get this D and convert it into percentage. So this is the only concept which is applicable here. Now let's move to the next question, which says a PV module is interfaced with a battery and a load as shown in the below figure. So this is our battery here. This is our PV module. All the transistors have an on state voltage drop 0.2 volt, VC and VB state. It is like base, emitter and collector. So it is between this collector and emitter, and this is between this base and emitter. The ratio of the emitter current to the base current under the on state is 30. It is already given. The ratio is given. A logic circuit is implemented to switch off the transistor for the following condition. Conditions are the same which we have already seen. When battery is VB, battery voltage VB is greater than this 14 volt, the transistor T1 will be made of. It means here 14 is the Vmax, the maximum voltage of the battery or in the charge state. So this will be switch off, this particular switch. When the battery voltage VB is less than the 11 volt, so this 11 volt is the V minimum when battery is fully discharged. Then the transistor T3 will be made of. It will made of. It means our battery will be connected to the PV system only. And when battery VB is between these two, V minimum and V maximum, both transistor T1, T3 will be kept on. So it is the same thing which we have already seen. What are the logic of a charge controller which is being used here. If the maximum emitter current allowed is 2.5 ampere through all the transistors, so it is the limit of the transistor, then what is the minimum value of the resistance R2? It is asking the minimum value of the resistance R2. R2 is where? Here. And these are the options. Think about this. How can you do this? First write the expression of this R2. Okay, no one writing. I'll write them. See, we have, this is the source of 1 voltage. 1 voltage will be here across this, 1 voltage will be here across this. So this is a closed circuit here. This particular circuit is closed like this. So the maximum current which can flow through this R2 is I R2 max will be how much? Voltage of PV minus voltage across. See, this is base, this is emitter, this is collector. This is emitter, this is base, this is collector. Voltage T2 across CE, voltage CE T2 minus voltage VE T1. So this is the 3 voltage, and then the leftover voltage will be across this R2, and the current will be divided by R2 minimum, because then it will be the maximum current. So this is a particular equation we have. Then what is given? We have given that the current through the transistor can be maximum 2.5. Where it is given? It is given here. And also there is a ratio is given. So IE, emitter by base, it is ratio given is 30, and this emitter current is given 2.5. Then IB will be equals to 2.5 divided by 30. How much it is? Just divide 2.5 divided by 30. Okay, 0.083. Okay, so one more equation we can write here in terms of I, that will be I across R2 maximum will be equals to how? We have IB here, current flowing from here, IB. In terms of IB plus the voltage across these terminals divided by 100, that will be the current that can flow through this resistance. So we have I equals to V by R, voltage is VBE divided by 100. 100 is the resistance. So how much it is? 0.083 plus 0.7 divided by 100. So how much it is coming? 0.7 divided by 100 plus 0.083. 0.09, and if like we consider more, it will be 0 only. So this is the IR2 maximum. So we have got this value, we can put this value here and can get the R2 value, minimum R2 value. So using this, in this equation, we will get R2 minimum equals to VPV minus VCE T2 minus VBE T1 divided by IR2. What is this VPE is? What is this? VPV is. See, maximum current flow through this R2 will be equals to when the PV voltage or the battery voltage will be at the maximum condition. And this maximum condition will be equals to what? We can say this CE. We have a voltage here. We have a voltage here V. We have a voltage here V. And we have a voltage here V. So this V is given in the charge condition is 14. Maximum condition. Yes, terminal voltage, right. So this terminal voltage will be this plus this. How much it is coming? 14 plus 0.2. So it will be 14.2 minus 0.2 minus 0.7. B already given. What is the value you got for this volt resistance? Oh, sorry, current 0.09. 0.090. Solve this, you will get the R2 minimum. What is the value you are getting? (14.2) minus 0.2 minus 0.7 divided by 0.090. 147.7. Yes, we are taking less points, so it is coming 147.7. So which match is there? This B. So B is the correct answer. VB is the correct answer. Okay, next question says, similar to the question 5, what is the minimum value of resistance R9? Now it is asking for this resistance. Before we were doing for this, now it is asking for the R9. See here, now just write the equation for, okay, these are the options. So for this particular condition, I have This is not the, this is right. 145 ohm. Okay. 145.25. Let's see. Okay. So now let's see. This is a closed loop like this, and can write the equation in terms of this IR max. So IR9 max will be equals to VB max minus V, same here, VCE and EBC. VCE T4 minus VBE T3 divided by R9 minimum. See, all the components are same, so you will get the same current for the R9. So that current will be using like 0.90, I guess. This was the current we got. So because all the components value and everything is same, so we are not solving it from the starting, so we will get this current as IR9. But only one thing is there. Here it is not PV, it is VB max, and VB max is what? So R9 minimum will be equals to VB max is 14 minus 0.2 minus 0.7 divided by 0.090. So this will be the value of this. How much it is coming? 145.5. So this D is the right answer. You just need to do the circuit completion here only. Let's move to the next question, which says at the maximum power point of photovoltaic module, dI by dV equals to, these are the options. You just need to tell me this dI by dV will be equals to what at the maximum power point condition. Okay. Rajnikant said minus 1 by V, it means C. Rashmi also said C. Okay. So yes, you are right. It is like this. This is the IV curve, and this is the maximum condition, P max, and P max will be equals to VT into IT, because it is terminals. That's why we are saying, Rasmi also said, Rami also said C. Okay, it is like VT into IT. So we will do dP by dVT will be equals to IT plus VT into DIT divided by dVT, and at this particular point delta P by delta VT will be 0. It is like this. This is a flat on the PV curve. This is IV curve, this is PV curve, this is flat, slope is 0. If slope is 0, dP by dt will be 0, equals to IT plus VT DIT divided by dVT. So it is asking dI by dV will be equals to minus IT divided by VT, and we can write as minus I divided by V, minus I divided by V. Yes, you are right. Answer is C. Let's move to the next question, which says advantages of using a simple charge equalization circuit based on resistive attenuator are. These are the options. It is asking the advantages. Simple resistive attenuator. Matlab, like it is like this. We have a battery, then another battery, then another battery. So we simply have a resistance here, resistance here, resistance here. This is the circuit which we use. It is asking the advantage of using this particular circuit. Rasmi said B, robust in nature, simple in implementation. I agree. Okay. Rajnikant said B. Okay. So do you think the some other options are also right? It may be a multiple choice question. There may be more than one answer. Okay, then identify those options as well. Okay, B and D. It can easily scale for large battery. I agree. D. Okay. What about A? See, one battery, one resistance. We have one component only. Yes. A, B and D. A, B and D. What about C? Yes, that's the disadvantage. It is dissipating. So we have correct answer A, B and D. Right. Next question. It says the figure shows the implementation of the functional logic of charge controller where the symbols have their usual meaning. It means S represent the switch. This is PV panel. This is battery. And S is the switch. Let the battery voltage be VB. So it is saying it is VB. The maximum battery voltage is Vmax. Vmax is the maximum. Minimum is the V minimum. Then which of the following logic is correct for the implementation of charge controller? Here also there may be multiple choice answers, so be careful. Switch are unit external, load is always connected to the either source. So these are the options. At what condition which switch will be on, which switch will be off? You need to identify it. Rajnikant said C. C, where S1 is on, S2 is off, and S3 is on. When VB is between Vmax and V minimum. Okay, do one thing. Simplest thing. Identify for charging. When battery is charged, when battery is fully discharged. First identify what is the condition when battery is fully charged. The VB should the condition when battery is charged fully, it means VB is greater than Vmax. When battery is discharged, okay, I'm just seeing your responses C, D, A. When battery is fully discharged, the condition should be VB is less than V minimum. So in this particular condition what should be connected? PV module and load. This is battery, this is load. When battery is fully charged, so what do you think? It should be connected S2. See, when battery is fully charged, only load should connect. When battery is discharged, only PV should connect. Okay, so when it is greater than Vmax, it means it is fully charged. S1 is on. S1 is on, it means it is connecting with this PV and it is only fully charged. So this condition should not be there. What do you think? As it is fully charged because VB is greater than Vmax, S1 is on, S2 is off, S3 is off. Yes, so first will not be there. First is not the right answer. Okay, now let's see the B. Rasmi is saying B. Let's check this B as well. B is saying S1 is on. B is saying VB is lower than the V minimum. It means it is fully discharged. So S1 is on, it is connecting to the PV, S2 is off, load is not connecting with the battery, and load is connected with the, sorry, I made a mistake. Battery is here only. Battery is here only. This is the battery. This is the capacitor. Okay. Yes. S1 is on. Replace PV with the PV with battery. Why we need to replace? Yes. Discharge condition is that we are not connecting with this batteries connecting to this PV only. So it is being charged. While it is discharging, it is not connecting, right? Okay, so B is saying S1 is on, S2 is off, so and S3 is on. You wrote PV instead of battery. No, battery is here. I wrote PV for this. Only PV, not only battery. Okay. Only PV, not only battery. No, I have written only load here. I'm saying if battery is fully charged, so PV should not be connected. It should be connected with the load only. Okay, if you're having confusion, you can have a look here as well. So these are the scenarios which we have also shown in the first time. So this is the condition when it is fully charged. So means this is connected with the load only. When it is fully discharged, it is connected with the PV only. When it is not, it is in between, it is connected with the both things. So this is the thing we need to identify. So this VB is lower than V minimum. This is the condition. And in this condition, this will be on, this will be on. This is on, this is on, this is off. It means S1, S3 on, S2 is off. Yes. Someone said B is the right answer. Yes, B is the right answer. Now let's see C. S1 is on. Yes. S2 is off. S2 is off. S2. This S2. S2 is on here. S3 is on. S3 is off here. So no, C is not the right answer. Let's move to the D. S1 is on. Yes. S2 is on. Yes. S3 is off. Yes. So D. B and D. Who said B and D? Yes, Vikas, right. Someone also said B and D. Yes, Rasmi also said B and D in starting only. So yes, B and D are the correct answer. Now let's move to the next question. For as shown in figure below, a charge pump based charge equalization circuit is implemented for a series of connected batteries. Nominal voltage of B1, B2 are the 15 volt. If the reverse blocking voltage capability of the diode is 40 volt, then the voltage across the reservoir capacitor CR can be. These are the options. The capacity here is 40 volt. The battery is 15 volt. This is 15 volt. Then voltage across this reservoir. This V. You need to identify. Ten volts. Yes, consider it's like positive, negative, positive, negative, positive, negative. So those are connected in a series condition. So it will be like 15. Okay, I'm writing in the terms of equation. VB1 plus VB2 plus V across CR will be equals to 40. That is the limit. We have 15 plus VCR equals to 40. VCR will be equals to 40 minus 30 equals to 10 volt. So 10 is the answer. So we are done with the all things. So if I just want to say, if you are not following the weeks, if you are not following the lectures, so come after watching the lectures. It will be good for you as well. So this is end of this lecture. We will meet in the next class, that will be on the next Friday at 6 p.m. and I am going to upload this video in like 15 minutes. I'm just, thank you everyone. If you are new here, I am just giving you the link. If you have missed earlier classes, or if in the future as well, if you are like not able to come on the time, then you can go through the lectures. This is the link. Thank you everyone. Good night everyone. Good night Rajnikant.